Calculus. This may be our last video, unless I find some helpful hints or some problems to do later. At least the last bit of information that I want to stuff into your calculus brain. 426, you'll be observing this at or after 426. And we're finishing up with some various integrals that have fallen through the cracks. And the ones I want to talk about harken back to the derivatives of the inverse trig functions. So I wrote those out. We already have done these. The derivative of the arc sine of u, which is an expression in x over a, is this. And arc cosine, arc tangent, arc cotangent, and then there's two more, arc secant and arc cosecant. Not sure they all show up real well in this screen. I'll zoom in on the last two just to make sure you can get them all. Alright, so there we have the 6 that we've already had previously, and we've practiced problems according to those. So when we switch over to integral land, we need to look at one at a time here. So let's say we're looking at this one. Hope you're not getting too seasick here. Alright, when we look at this one, we're going, if the derivative of this is this, the integral of this must get us back to that. And so it does. So the integral of du over square root of a squared minus u squared is the arc sine u over a plus c. Alright, so if we look at arc cosine, the only difference between the derivative of the two is the negative sign. So if a negative sign appeared in this, we would just pull it out and do it this way. So we don't really need to find the integral of the negative of this. It would be a correct way to express it, but we'll just go ahead and use the more obvious arc sine if it's negative. Alright, so then I'll skip that one and go down to arc tangent. So the integral of this would get us back to that. So this should make sense. So the derivative of what was the so the integral of what was the derivative will take us back to the original expression. The only thing is I pulled out the constant 1 over a. So let's see. This a, let me see about that. Arc, the derivative, the integral, 1 over a squared plus u squared. Oh yeah, that's right. So this is correct. The derivative of a squared plus u squared is 1 over a arc tan u over a plus c. So we have to do a little bit of u substitution to see that that was correct, but it is. Alright, once again we're going to skip the negative one, which can be handled easily with this integral, and skip down to this one, where we take the integral of this, and we get that 1 over a business because we have to account for that. So this is the integral. 1 over a secant inverse. Notice you can write it as arctangent or secant inverse. Absolute value u over a plus c. Alright. Arc cosecant, because its only difference is the sign, a negative sign, we'll go ahead and just use this version. So these three we have to kind of keep our eyes out for. So whenever you have an integral and u substitution doesn't work and nothing else seems to work, have your eye out looking out for a constant squared minus a variable squared. And under the square root, or a constant squared plus a variable or expression in x squared, or this form. Just have your eye being, looking for that and recognizing that these would be inverse functions that you're integrating. So let me see if you can pick out one. Let's do an example. So the example is the the integral of dx over the square root of e to the 2x minus 2. All right, that's the e to the 2x there. So I'm going to recognize that that's lining up to be one of these. So I'm going to start out by saying what u would be and what a would be. So u would be e to the x, because when you square u, you get u squared, and squared e to the x, you get e to the x raised to the 2, which is e to the 2x. So my a is going to be 1, and my u is e to the x. So let's substitute everything back into here using a's and u's, so we can easily fit them into the forms I just showed you. So once you find u, you have to do a du, and then substitute everything back in. So here, when I have e to the 2x, I'm going to put u squared. Here, I'm going to put a squared. And what am I going to put up here for dx? Well, I don't see dx exactly, but I see a dx here. So I'm going to solve this expression for dx so I can make a complete substitution. Divide both sides by e to the x, and now I have an expression for dx. So now I can substitute dx with this expression, and I can substitute everything else with these. So when I do that, my problem that did look like this now looks like this. Du over u is my dx, and then square root of u squared minus a squared. And now that is exactly like this expression right here. So I know that this will be the answer. So I come back down and I write the answer out just as the formula says, but then I substitute back with x's and numbers. So my a is 1. There's no, my a up here was identified as 1. So 1 over a is still 1. Secant inverse u was e to the x over 1 plus c. So I can drop all those 1's, and that is my answer. So this was an inverse secant problem. All right, let's try one more. All right, write down this one, and right off you can see that if we wanted an a squared minus a u squared, our a would be 2 and our u would be x. But this x plus 2 is troublesome. So you may recall, and hopefully do, that when you have two terms divided by 1, you can rewrite that as the first term divided by this plus the second term divided by this. So we're going to make it into two integrals. So notice how I did that. This term divided by this plus this term divided by this. Mathematically sound. Now, one of these is an inverse situation, an inverse trig situation. One of them is not. So the way I can tell is I always try u substitution, and if it doesn't work, then I look at inverse trig. So u substitution, I would suggest to myself, let me cover up this side here. We'll just work on this integral right now. U would be this expression under here, so du would be minus 2x dx, and I have an x in here to substitute for. Here's an x, so I'm going to re-situate this for x. So when I do that, I guess I did that outside the box, so my box was too small, but I solved x, and actually x dx is du over negative 2. So I went from that expression to one that had an x dx, which is in my problem and needs to be substituted for. Alright, so now I'm going to substitute everything up in this expression. My x dx takes on du over negative 2, and the square root of u is there. So let's see. So we have all the substitutions made. This can be rewritten by taking the negative 2 across the integral sign, and this square root of u can be written as u to the minus 1/2. And now I have something familiar to integrate, and I go ahead and integrate it, adding 1 and dividing both sides by 1/2. I have a negative u to the 1/2, and I can substitute back because u was 4 minus x squared. So there I sit. So I didn't need any inverse trig on that side. Probably it'll appear on this side. Alright, let's go down the other side then. The integral of 2 over 4 minus x squared dx. If I'm looking for trig, inverse trig, I say a is 2, so it'll be a squared minus u squared, u is x. So when I do that, and I should say du is dx. Forgot. So now I substitute everything in. I have the 2 coming across, leaving a 1 over a squared minus u squared. And I should have a du. Sorry. Alright, now that's one that I recognize from what I learned today. And that's the inverse sine form. So I just go and create the inverse or arc sine u over a. It matches it exactly except for the 2. Now I go back and put x's for u and 2's for a, and I get 2 sine inverse x over 2. My final answer then I can put together down here. Alright, so some expressions that look similar to what we have been working with actually work with u substitution. Some will require that arc sine, arc tangent, or arc secant. Okay, hopefully that will help you in your practice problems. And to finish up, sad but true, we are going to look at an integral that I cannot teach you why it is what it is until we learn something called integration by parts. It's not required by the AP exam, and after the AP exam I will teach it to you. So for now, I want you to memorize the fact that the integral of ln of x dx is x ln of x minus x plus c. And I will show you why that is another day. So, taking that, we can also figure out what is the integral of the log to the base a of x. So, this is another one that we can do. So, we recall from our pre-calc training, we can rewrite any log to any base to ln by saying ln of the upper divided by ln of the lower. And so I rewrote it that way. ln of x over ln of a. These are equivalent expressions, and we proved that in pre-calc. Now I recognize ln of a is just a constant, so I'm going to kick it out of my integral, where it'll sit out in front as 1 over ln of a. And now I have the integral of ln of x, which I just explained to you or told you about up here. So now I can just finish with that expression. 1 over ln of a times x ln of x minus x plus c. Alright. I don't know if that has a glare. Let me move it over. 1 over ln of a times the expression x ln of x minus x plus c. Alright. Few things to memorize. Just a few. Alright, class. Over and out, carry on.